So this is the second part of the phase diagram lecture. In the first part of the phase diagram, I have explained to you about what is phase equilibrium, and then we have seen some of the very basic phase diagrams of binary systems like binary isomorphous system, binary eutectic system. And in this particular lecture we will see that what are the other kinds of binary system, and specifically we want to discuss iron carbon diagram in detail. So objective of this lecture is will be introduced with intermetallic compound. We'll see the different kinds of invariant reactions that we generally see in iron carbide phase diagram, and then we'll see in detail and try to remember some of the important temperatures and compositions in the iron carbide equilibrium phase diagram, and finally we'll see what are the effect of other alloying components other than carbon in the steel. Okay, so as we have already seen that some of the primary phases, some of the primary solid phases are produced because of the solid solution. That means in this diagram you can see this is a diagram of magnesium and lead. Okay, so when lead is mixed with magnesium, you can see that only a few percentage of lead will go into magnesium. Okay, so lead or magnesium having limited solubility, they do not have extensive solubility. Okay, so that is very clear from this. That is clear from the solubility curve, that for example at 300 degrees centigrade only this much of lead can go into the magnesium. So it's a limited solubility, but within this region it is a single solid phase. That means at higher temperature you can see more and more lead can go into magnesium and produce a primary phase solid solution. Okay, so this is a single phase or primary phase. Okay, similarly we can see another primary phase is also there on the other hand here, where if you try to mix magnesium into lead, suppose there is lead and you try to mix magnesium, and we can see it's a very limited solubility, and only even at a very high temperature you can see only few percentage of magnesium go into lead, but still some amount can go into lead and will form a single phase solid solution, and that is the beta phase. So this alpha phase, which is the magnesium rich phase, or the beta phase, which is the lead rich phase, these are primary phases in this diagram. Okay, what are the other primary phases present? That is the liquid. So at very high temperature above melting points, or you can see in this region, you can see at liquid state they are forming a single phase. So how many primary phases we can see in the magnesium and lead diagram? That is this binary system having alpha, that is one solid phase which is magnesium rich phase, liquid, another one is lead rich phase, that we can see. So what we have observed, that magnesium or lead both have the limited solubility in one another, and that is why this kind of phases are created. But one interesting thing you can see in this diagram, here you can see if you mix 80% lead and 20% magnesium, you will find that they will form a solid solution and forming a single phase. Okay, so this is a speciality of this binary system, which is combination of magnesium and lead, that they have primary phases there at the very a small amount of when lead is mixed with magnesium, that is the alpha or beta. Similarly, but intermediate percentage of magnesium and lead, here you can see that is 80% lead and 20% magnesium if you mix at that specific composition. That means it is not happening, this solution is not happening over a huge range of values of the lead, only very specific, maybe this 80% and around it maybe it is 79.8 to 80.2. So it is happening within a very small range, such that you can thought of as if a specific composition can only go into the solution and forming a single phase. So that has been shown as another phase by this red vertical line. So this red vertical line basically indicating another solid solution of lead and magnesium, where the percentage of lead is fixed, almost fixed 80%, because this is happening over a very close tolerance of lead or magnesium. So this is another primary phase that is present in the magnesium lead binary system, and this is what is called intermetallic compound. Why the name compound? Remember, this is not a chemical compound, this is not a chemical compound, this is actually a solid solution. But since this is happening at a specific percentage of lead, as if you can write this as this formula. Okay, so this is what is the idea of intermetallic compound, that it is basically a solid solution primary phase, but that happens at some intermediate composition within a very close tolerance, such that you can given a formula name of that. Okay, so this is basically that thing. Mg2Pb is basically a solid solution of magnesium in lead, happening only at 80% composition. So how many primary phases you have observed? Alpha, beta, and this one. This one is another primary phase. This is intermetallic. Generally they are very hard and brittle in nature. Okay, this intermetallic compound. And what you observe that in the left side of this intermetallic compound is a kind of eutectic system has been observed, and on the right side you see another eutectic system observed in case of magnesium lead system. So this is the speciality of the magnesium lead diagram. So the main takeaway point from this slide is that we have to understand that what is intermetallic compound. So this is basically a solid solution, not actually a chemical compound, generally very hard. Remember, it's a single phase solid solution and occurring at some intermediate composition. Okay, now let us see some of the other binary systems other than eutectic. So already we have seen this eutectic system, if you remember. So what was eutectic system? If a liquid upon cooling forming two solid phases. So this is basically what is the eutectic system. The basic guideline of the eutectic system is what? When liquid upon cooling will form two solid phases, and if you remember, the two solid phases when they form, they will be in the form of a lamellar structure. Okay, so this is the basic thing of the eutectic system. Now in iron carbide phase diagram, we will see this kind of eutectic system is also there, and that happens at 1147 degrees centigrade, where liquid will be converted into some solid phase and Fe3C, another solid phase. So we'll see that in the phase diagram, then you definitely understand what are these things. Okay, but other than eutectic, what are the other different invariant reactions? But before going to the other kinds of invariant reactions or invariant transformations, let us see that what is the degree of freedom of this eutectic reaction. If you remember the Gibbs phase rule, that was what? P plus F is equal to 2 plus C. But why we have written 1 instead of 2? Because we are not considering pressure as the thermodynamic variable. That means we are considering pressure is constant, say atmospheric pressure. So only thermodynamic variable present is the temperature. So instead of 2, we are only considering 1, because temperature is considered only thermodynamic variable. Okay, so P plus F is equal to 1 plus C is the modified phase rule. Now at the eutectic system, if you remember in the eutectic system is like this, where this was the liquid, and maybe in this region alpha plus beta will be formed if you cool from this position, right? So this was there in the thing eutectic system. So here you see how many phases are in equilibrium. Here you can see the liquid phase is there. If you find that alpha phase is also there, and here you will find the beta phase is there, right? So here it is liquid plus alpha, here it is liquid plus beta. So at this point, liquid, alpha, beta, all these are in equilibrium. So how many phases are important in equilibrium? That is alpha phase, beta phase and liquid. So 3 different phases are in equilibrium at this point. Okay, how many components? It's a binary system, so number of components are 2. Now if you put this P and C value in this expression, what you are getting? You are getting that degree of freedom is 0. Degree of freedom 0 means you do not have in your hand, so everything is fixed. That means the eutectic composition is fixed, eutectic temperature is fixed, so everything is fixed. Okay, so that is why the degree of freedom is 0. And since the degree of freedom is 0, that is why the name is given invariant. This invariant reactions, this invariant name came from the fact that degree of freedom is 0, or you can thought of in that way because during this transformation there is no change of temperature. Temperature remains fixed during this change from liquid to this, and that is why, since the temperature is constant, that is why it is called invariant. So the two way you can give your logic. Now see the other kinds of binary systems. Those are possible. Another transformation that is also invariant transformation, which is called the eutectoid. In the eutectoid transformation, what happens? That one solid upon transformation converted into two other solid. So let us consider S2 is one solid, and that will be converted into a mixture of two solids. So again the idea is basically the similar. Let us consider some solid is here, that is S2, and ultimately that will be converted into combination of two solids, S1 and S3, like this. Okay, so this is what is the idea. So similar to eutectic, here also a lamellar structure will form of S1 and S3. Okay, this combination of phases will be present here. So one solid will be converted into two solids. Okay, this is what is the eutectoid. So again you can check this will be valid because 3 phases are in equilibrium, S1, S2, S3, 2 components are there. So again the degree of freedom is 0. So all these different kind of reactions or the transformation that we are considering are all invariant reactions. Okay, now see, and in our iron carbide diagram we will see one such transformation equation where austenite will be converted into ferrite and cementite. We will see when we will go into the iron carbide phase diagram, then you will understand. Now another one, which is the peritectic. Okay, peritectic reaction is basically another invariant reaction where one solid and liquid that will be converted into another solid. So if you cool it, it will be converted into S2, and if you heat it, it will go in the opposite direction. Similarly, so this one will also, if you cool it, will be converted into this one. So one solid and another liquid and by their combination ultimately, and during this transformation again the temperature remains constant, degree of freedom is 0, everything remains same. And in iron carbon diagram we will find one such reactions. Okay, so eutectic, eutectoid and peritectic, these are the three most important invariant reactions present in iron-iron carbide equilibrium phase diagram. Okay, and we'll see where those three transformations are occurring in iron-iron carbide diagram. One more thing, this is a monotectic where one liquid will be converted into liquid plus solid. Okay, so this is what is the monotectic reactions, and we'll see that such monotectic reactions are also happening in case of iron carbide diagram also. So let us concentrate on this iron carbide diagram. Okay, now if you listen my lecture very carefully, you will find sometimes I am telling it is iron carbide diagram and iron carbon diagram, and sometimes I am telling it is iron carbide diagram. So it is a iron carbon diagram or iron carbide diagram. Actually, if you see the phase diagram of iron carbon diagram, here you will find in the x-axis it is basically composition of carbon, that means weight percentage of carbon is given here, and you see 1%, 2%, so only up to 6.7% it is given. So if it is a full iron carbon diagram, it should be from 0 to 100% carbon, right? That we have seen in other cases. But after 6.7%, nothing is given in the iron carbon diagram. So this is basically a portion of the iron carbon diagram up to 6.7%. And if you remember the example with which we have started this lecture of magnesium and lead, there was one intermetallic compound, one intermetallic primary phase was present. Okay, and that was happening at a a composition of 80% lead. Similarly, in iron carbon system, at 6.7% of carbon, one intermetallic phase is present. Okay, and that intermetallic phase is this one. So this line corresponds to that intermetallic phase. Okay, so this one is the intermetallic phase. So 6.7% carbon, and this is again, since it is happening exactly at this percentage of carbon, you will find that iron is going into the carbon and forming a single phase. And generally these phases are very hard and brittle, and this one is called cementite. Okay, Fe3C. This can be symbolized as Fe3C, but again remember, this is not a compound, this is not a chemical compound, this is a solid solution of iron and carbon, but this solution occurs only at a specific composition, that is 6.7%, some intermediate composition. On the other side of the iron carbon diagram actually are not so important to the engineers. The reason is that if the carbon percentage is too high, that is more than 6.7%, they become so brittle that they are not at all suitable for the structural purpose. That's why engineers prefer only this portion, and that is sufficient for all of our practical purposes. So truly speaking, this particular diagram is only a portion of the iron carbon diagram, and which is called iron carbide diagram. This one is nothing but the iron carbide or the cementite. That is why this is the iron carbide diagram. This is the name of this diagram that we have to learn how to draw. Okay, now we have to start from the upper portion, and you have to remember this diagram. Okay, this is very important diagram to all the mechanical engineers and civil engineers. Okay, because you know that steel is the most important material for the structural purpose as well as for the machine components. So that's why for civil and mechanical engineers, iron carbide diagram is iron carbide diagram is very important. Now we have to learn how to draw it, and what are the things that we have to remember, that we'll see. So let us take some other colors, say green color. Now first of all, look at this portion of the diagram. You have to remember this temperature. What is this temperature? This temperature is the melting point of iron, pure iron. This point corresponding to pure iron. 0% carbon means pure iron. Okay. So this is again a binary system where what are the two components? One is iron, another one is carbon. Okay, it's a binary system, and here it is a 0% iron, 0% carbon. So this is nothing but the melting point of iron. So what is the melting point of iron, pure iron? That is 1538 degrees centigrade. Very important temperature, you have to remember. Second important thing that you have to remember is something happening at this position. You see, let us first try to find out what are the primary phases present in the diagram. The primary phases present here, you can see this is the liquid phase. So this region is the liquid region. Here you see one primary phase present in this region, which is delta phase. This is called delta ferrite, delta iron. Okay, delta ferrite. I have told you different solid phases are actually represented by alpha, beta, gamma, delta. These are the different symbols used. So this one is the delta iron. So this delta phase occurs at a very high temperature. You can see that above 1400 degrees centigrade or above 1394 degrees centigrade, you will find that carbon is going into the iron and forming solid solution in this region. Okay, so this is delta iron. The structure is, it's a BCC structure, body centered cubic structure. The delta iron having body centered cubic structure. Now one very important thing that you have to remember, this part first. Okay, let us draw this part. Now three important points, 1, 2 and 3. The composition of these 3 points are important. What is the composition of this point? The composition of this point is 0.1%. 0.1%. 0.1% carbon. What is the composition of this point? Composition of this point is 0.18%. And composition of this point is 0.52, say 52, 53 or 55, say 0.55%. So these 3 points that you have to mark, and what you have to do, you have to join this line and this line. Okay, then this phase, this single phase which is delta iron, can be easily identified, and you have to draw this line and you have to join this one with the 1394 degrees centigrade. This temperature is 1394, very important temperature. You have to remember. You have to remember this temperature, that is 1493. So in this region, what you have to remember is that 3 temperatures. One is this, that is melting point of iron, 1538. This temperature, that is 1493, and this temperature, which is 1394. Okay, now here if you see, this region is liquid, right? This region is liquid. Everywhere here it is liquid, and here it is delta. So what will be there in this region? So this region, it is basically delta plus liquid. Here it is delta plus liquid. So this region is delta plus liquid. Okay. Now here you see, if you extend this like this, and you see at this point what is happening. This is another solid solution of iron or carbon in iron. Okay, so you can see this particular solid solution, this is again another primary phase. So we have seen one primary phase which is happening at a very high temperature, more than 1394 degrees centigrade. Another which is in between this range, this region, which is called austenite or gamma iron. Okay, so gamma iron is another single phase solution occurs, and that is in this region. So this region again another solid solution or primary phase, but the structure is FCC. I have told you that delta is a BCC structure, delta iron is a BCC structure, but this one is FCC structure. Okay, face centered cubic structure. Now if you see at this point what is happening, at this location what is happening, here you see the situation is like this, that sorry, let me try it again. So here you can see here it is delta plus liquid, and here it is solid phase austenite. So what kind of reaction taking place here? That is delta iron plus liquid was there, and upon cooling, if you cool it along this line, then it will form a single phase solid solution which is gamma. So one solid phase plus liquid upon cooling taking place, it will lead to austenite or the gamma iron. So this is again on invariant reaction, if you remember. So this is basically the peritectic reaction that happens at that point. So what is the temperature at which it happens? 1493 degrees centigrade. It is delta, that is the delta iron plus liquid, that upon cooling will be converted into austenite, gamma. Okay, so again this is an invariant reaction that is happening here. So this is peritectic reaction that is happening at this position. Clear? Now what you have to remember, the second stage, this portion, you see what is the composition? That is 2.14%, and this composition you have to remember 4.3%. Okay, so you have to join these two here, and that you can extend up to this line where it is basically the cementite. Remember, this whole line corresponds to Fe3C. This line corresponds to Fe3C or cementite. Now if you see at this region, what is there in this region? Here it is austenite, here it is liquid, so this region is austenite plus liquid. What is there inside it? Here it is liquid, and here it is cementite. So this is liquid plus Fe3C. So at this point, basically this liquid, austenite and Fe3C are in equilibrium. So along this line, another invariant reaction is taking place. You see what is happening? The liquid is converted into what? Austenite and cementite. So two solids are forming from liquid at a constant temperature. Okay, so this is what? This is nothing but the eutectic reaction when liquid converted into two solids upon cooling. So this is eutectic reaction which is happening at 4.3% of carbon. So here this is happening at 0.18% carbon at a temperature 1493. Okay, so eutectic reaction is taking place here, and remember, when the eutectic reaction taking place, the laminar structure will form of alternate layers of austenite and cementite. Now you come to this particular position. Here what you have to remember, here you can see, you have to remember temperature is 1147 degrees centigrade, this composition 4.3, this composition 2.14, and definitely this composition 6.7%. Now come to this point where if you see this one is austenite. Here you can see another primary phase in this region. You can see the carbon go into the iron and forming a single phase in this region, and this is what is called alpha iron or the ferrite. This is called the alpha iron or ferrite. Okay, so this is the alpha phase, another primary phase in this region. Okay, so here you can see one solid phase, primary phase, which is austenite. Here one primary phase that is happening at lower than 900 degrees centigrade. So how many primary phases you can see here? One is delta iron, which happens at very high temperature, more than 1394. Another one in between 912 and this, within this range you can see, and another one you can see at a lower temperatures. Okay, so that one is the alpha iron or the ferrite, and the crystal structure of the alpha iron is again BCC, similar to this one, but obviously they have different lattice parameters, but BCC structure again. Now and I have not told about the structure of cementite. Remember that cementite is orthorhombic crystal structure. Fe3C, this is having orthorhombic crystal structure. Now if you see what is happening at this position, here it is gamma, here it is, let's take this point. Okay, here it is gamma, in this region it is alpha. So what will be there? It is alpha plus gamma. So this region is alpha plus gamma. Now here it is austenite, and here it is cementite. Okay, so basically at this position what is happening, this alpha, austenite and cementite are in equilibrium. Okay, so when from here to here the transformation takes place, which is again happening at a constant temperature. So what kind of transformation is taking place? If you see the transformation that is taking place here, where one solid phase austenite, that upon cooling, this austenite upon cooling transformed into what? Alpha and cementite. Alpha plus cementite, Fe3C. So at this position this is happening, and this is what kind of invariant reactions? We have seen it earlier. This is Eutectoid reactions. So in Eutectoid reaction, you know, austenite upon cooling will convert it into alpha plus Fe3C. At which temperature it is happening? It is happening at 727 degrees centigrade, which is called Eutectoid temperature. So this is what is the eutectic temperature. This is what is the eutectic composition. This is Eutectoid temperature, that is 727 degrees centigrade, and this one is Eutectoid composition, which is 0.76% of carbon. These are the things that you have to remember. And what is the composition of this point? That is 0.022% of carbon. That you have to remember. Here you have to remember what is the temperature, that is 912 degrees centigrade. Okay? And this temperature you have to remember 1147 degrees centigrade. And here it is coming from room temperature. If you see that at room temperature, though it is showing at 400 degree, but at room temperature this carbon percentage is 0.008%. So at room temperature the carbon percentage is 0.008%, where it will cut. So it is almost coincide with the vertical axis. Anyway, these are the important coordinate that you have to remember. And what is the composition? Here the composition is 0.76. In many books you may find, for simplicity, it has been written as 0.8%. So Eutectoid composition is called 0.8%. It is okay, no problem, but to be very specific, it is 0.76%. Okay. And again remember that due to this Eutectoid transformation, lamellar structure of alternate layers of alpha and Fe3C will form. Okay, so this is what is called the pearlite. So, and we'll see what are those things in detail. Few more things that we can see at least in this diagram, that if you see these green dots indicates the structures. What is the structure here? It is austenite. It's a solid phase, so the structure is like this. These are the grain boundaries and this is austenite. Now after transformation, exactly at the Eutectoid composition, Eutectoid transformation takes place. That means alternate layers of ferrite and cementite will form, and here you can see that structure. So it is alternate layers of ferrite and cementite, alternate layers that will form, and they also have phase boundaries like this. Anyway, so this is what is the pearlitic structure. So this is what is the pearlite. Okay, alternate layers of Fe3C and austenite. You will ferrite and austenite that you will observe. Now if you move through this region, that means if the carbon percentage is more than the Eutectoid composition, Eutectoid composition is 0.76, suppose you are at 1.5% carbon. Now if you heat it up to this much and then you are gradually cooling it, so at the austenite the composition will be like this. Now if you gradually cool it, then at this region what is the composition? At this region you can see some of the Fe3C will now form, because this is a two-phase region, and in this region what are the two phases present? One is austenite. If you draw the tie line you will get that. So here it is the austenite and here it is the cementite. So gradually cementite will start to form, and you can see the cementite has started to form. So some of the cementite that will form, and when it will go to this position exactly at the Eutectoid temperature, at that condition this austenite will having the composition exactly same as 0.76%. Remember, austenite and cementite will be there continuously as you are going down, but their composition will continuously change, that we have discussed in the first part of the phase diagram. So exactly when it will come close to this point, then the composition of the austenite will become 0.76. So if it further goes down, then 0.76% austenite will be converted into pearlite. Pearlite means alternate layers of ferrite and cementite. So in that case what will happen, if you see this structure, you will see that pearlite will form, and some of the austenites, pearlite will form, and some of the pro-eutectoid austenite that will also be there in the structure. Pro-eutectoid cementite that will be there in the structure, because these are the cementite. These are pro-eutectoid cementite. Pro-eutectoid means before coming to the eutectoid temperature, some of the cementite already formed. And here you can see one more thing, that these cementites are forming at the grain boundary region. The reason is very simple, that at the grain boundary regions are the defective regions, so they have the higher free energy. So when chances of nucleation of these solids, the probability will be more that they will form at the grain boundary region. That is why you can see at the grain boundary region, basically pro-eutectoid cementites are concentrated, and the remaining portion will form by pearlite, alternate layers of ferrite and cementite. Similarly, if you cool it in the left side of the eutectoid composition, then what you will find, that the pro-eutectoid phase that will form is not the cementite but the ferrite, because if you draw this one, you see that ferrite is the pro-eutectoid phase, and the austenite will be there, and austenite at this position will have this composition of the eutectoid composition, and that austenite will be transformed into pearlite, but some pro-eutectoid alpha phase will remain there. So some pro-eutectoid alpha phase or the ferrite phase will be there, and the remaining portion, that austenite, will be converted into pearlite. So pearlite will be there, and some pro-eutectoid alpha ferrite will be present. Okay, we'll see it in more detail in the next slide. But what we have identified, at least here, the eutectoid reaction is taking place, here eutectic reaction is taking place, and here peritectic reaction is taking place. Okay, and monotectic reaction you can call that is happening at this point, where liquid will be converted into gamma plus liquid. Okay, but the most important one is the peritectic, eutectic and eutectoid, but among them again the most important is the eutectic and the eutectoid. Now this portion up to, you can see the carbon percentage up to 2.14, this portion is basically the steel. That means the plain carbon steel. If you add carbon with the iron, we know that it's called steel, plain carbon steel, and that carbon percentage, if it is limited to 2%, then it is called steel. And steel can be hypo-eutectoid or it can be hyper-eutectoid based on its composition more than 0.76 or less than 0.76. Okay, now other part, that means if it is more than 2.14% up to 6.7%, this region is the cast iron region. So in the cast iron, this one is the most important reaction, which is the eutectic. In steel, the most important one is the eutectoid reaction. Now you see here, from liquid will be converted into two solids, that is austenite and cementite, alternate layers of austenite and cementite. So that particular structure is called ledeburite. Okay, so ledeburite is a structure, again alternate layers of austenite and cementite. Okay, so that happens exactly at 4.3%. But if you cool from this side, then what will happen? Here it is liquid, the whole thing is liquid. Here gradually pro-eutectic phase will form. What will be the pro-eutectic phase? The pro-eutectic phase is austenite. So pro-eutectic austenite will be there. But when it will come to this position, the liquid portion that will remain there, other than the austenite, pro-eutectic austenite, that liquid portion will have the composition 4.3%. So if you further go down, then that liquid will be converted into ledeburite. Okay, so in that situation, what will be the composition finally there? That is pro-eutectic austenite will be there. Okay, pro-eutectic austenite will be there, and what will be the remaining portion? That is the ledeburite. So ledeburite will be present there. Okay, and as you further go down, what will happen? That cementite will also come out, because the solubility, you can see, gradually decreases. Okay, so cementite will gradually come out in the mixture. Here also, if you see, if you cool from in this side, that means if it is hyper-eutectic, then you will find that what is the pro-eutectic phase? The pro-eutectic phase will be cementite. So cementite will be there, and what else will be there? That is the ledeburite will be there, because that liquid will be converted into ledeburite. So cementite and ledeburite will be there, and here what will be there? Pro-eutectic phase austenite will be there, ledeburite will be there, and cementite will be there, because gradually the solubility of carbon in iron is decreasing. That is why cementite phase will come out from that phase. Okay, so that is why austenite, ledeburite and cementite will present. Now if you further cool down, then what will happen? You see, in the ledeburite, actually what is there in the ledeburite? The ledeburite, basically it is austenite and cementite. But when you cross this particular eutectoid line, when you cross this eutectoid line, then within that ledeburite some of the austenites are present, and those austenite then undergo the eutectoid reaction and will convert it into pearlite. Okay, that is why the ledeburite will be transformed, and finally what you will get is that cementite will be there, and pearlite and transformed ledeburite will be there. Okay, so this is what going to happen if you go down. Similarly, in this region also the same thing will happen, that within that ledeburite basically pearlite is there, and that, within that ledeburite basically austenite is there, and that austenite will transformed into pearlite, and that is why the ledeburite will be transformed. Okay, so transformed ledeburite will be there in this region if you go below eutectoid temperature. Now see very clearly the most important thing in the iron carbon diagram that we have to remember. Here you can see there are two important points. The first one, the eutectic point. Where is the eutectic point? This is the eutectic point, point A. What is happening? Liquid is converted into austenite and Fe3C. Austenite and Fe3C. Clear? At which temperature it is happening? 1147 degree, 1148 degree or 1147 degree centigrade. This is happening. That you have to remember. And what is the composition of this liquid? The composition of this liquid is 4.3%. Fixed. Everything is fixed. Degree of freedom is 0. Remember. What is the composition of this austenite? 2.14%. Okay, 2.14%. What is the composition of this Fe3C? 6.7%. So everything is fixed. And what is the temperature? 1147 degrees centigrade. So everything is fixed. Now another one is Eutectoid reaction that is happening at point B. Okay, what is happening? Austenite is converted into alpha ferrite. You can see this blue colored alpha ferrite and Fe3C. Okay, so at which temperature it is happening? 727. You have to remember that this is happening at 727. What is the composition of this austenite? 0.76. You have to remember. Very, very important. What is the composition of alpha? The composition of alpha there is 0.022. What is the composition of Fe3C? 6.7. Okay, so these are the things that you have to remember. These are the most important reactions. For steel, this is the most important. In fact, for mechanical engineers, truly speaking, this part is the most important, the steel portion. So the Eutectoid reaction is the most important one. Okay, and the cast iron is also very important material, and for that Eutectic reactions is also very important. So now if you want to see the structure, you see at this point it is solid. Okay, austenite. So after that you can see it is the pearlitic structure. From the color you can understand that what are the phases. Here you can see this one is represented by the blue phase is represented by the ferrite phase, and the red phase is represented by the Fe3C cementite phase. Okay, so alternate layers of blue and red, that means alternate layers of ferrite and cementite, and this particular structure is called pearlite. Okay, and remember ferrite is very soft part, but Fe3C is very hard and brittle. Okay, and this is what is the pearlitic structure. Clear? And exactly similar kind of a structure you will observe here also, where liquid will be converted into austenite and cementite. So alternate layers of austenite and cementite will form like this, and that particular structure is called ledeburite, and this structure is called pearlite. This structure is called pearlite. And here when eutectic reaction takes place and it forms similar kind of a structure but alternative layers of austenite and cementite, that is called ledeburite. And under microscope the structure looks like this. Now if it is the hypo-eutectoid steel, hypo means if the composition is less than the eutectoid composition, that means if it is less than 0.76% carbon. Okay, so in that case how the microstructure changes. So here it is austenite, very simple. Now gradually when it will cross this line, then you will find gradually the solidification started. That means already this one is solid, but another phase, the alpha phase formation started. This alpha phase formation started where? Around the grain boundaries, because grain boundaries are the defective regions where free energies are larger, and by forming these probably the free energy will be reduced. So there is a spontaneous tendency that this alpha phase will start forming around the grain boundaries. So if you gradually go down, you see that around the grain boundaries lot of alpha phases form, and these are called pro-eutectoid alpha phase, because before coming to eutectoid temperature already this much of alpha phase has been formed. What are the remaining things? The remaining things are austenite. So remaining things are austenite. So what is the composition of that austenite? We can draw the tie line, and you see the composition of the austenite is nothing but 0.76. So if you further go down, that austenite will convert it into pearlite. Okay, that means alternate layers of ferrite and cementite. So here you can see, if you go down, that remaining austenite part now converted into alternate layers of ferrite and cementite. Okay, so this is what going to happen in the final microstructure of hypo-eutectoid steel if you gradually cool it. Okay, so under microscope you will find this kind of a structure. You see some of the pro-eutectoid ferrite state will be there, pro-eutectoid ferrite state will be there, and the remaining portions are alternate layers of ferrite and cementite, which is the pearlite. Now if it is hyper-eutectoid steel, then your pro-eutectoid phase will be cementite instead of pearlite. So gradually you can see the cementite particles will form at the grain boundary region, and here you can see these are the pro-eutectoid cementite that has been formed. Okay, and this austenite now having the composition of the eutectoid composition, because from the tie line you can find out the composition of these, composition of these. So if you go further down, then what will happen? This austenite will undergo pearlite, it will form pearlite. So you can see the remaining austenite, which is basically undergo eutectoid reaction and form pearlite. Okay, so this will be the final structure where pro-eutectoid phase is cementite. One thing you have to understand, that at this point basically the two phases are present. One is ferrite, another one is cementite. It is all the time, but the cementite are in two ways present in the structure. One is the cementite present, which is the pro-eutectoid phase, because before coming to eutectoid some of the cementite already has been formed, and another one within the pearlite in the form of laminar structure. So cementite, the whole cementite is not of the same form. One is in the form of pro-eutectoid phase, another one in the laminar structure in the pearlite. Now let us see what kind of problems are expected in the examination, or basically what we can find out. So suppose it is given that there is a steel whose composition is 0.4%. Okay, 0.4% carbon steel is there at a temperature just below the eutectoid temperature, just below the eutectoid temperature. So what we have to find out? We have to find out the composition of cementite and ferrite, because these are the two phases present below eutectoid temperature. The two phases present will be definitely cementite and ferrite. So the question is find out their composition. Okay, then you have to find out the amount of cementite present if there is 100 gram of steel. Okay, so you have to find out the weight fraction, you have to find out the composition. So these things we have already done, but we will see with respect to the iron carbon nickel. The amount of pearlite and the pro-eutectoid ferrite, that also we have to find out. Let's see. So the composition that is given is 0.4%. So 0.4% composition means it is hypo-eutectoid composition, right? Because 0.76 is the eutectoid composition. So we are basically here. So what is the overall composition? 0.4%. Okay. So what is the first part of the problem? You have to find out we are below eutectoid temperature. Below eutectoid is 727. Suppose we are at 726 degrees centigrade. Okay. So we are below eutectoid. So what are the two phases present? Obviously ferrite and cementite. These are the two phases present. So what we have done? We have simply drawn one tie line from this end to this end. So this tie line, two ends, will give you the composition of the two phases. So what is the composition of ferrite? The composition of ferrite will be, this is the ferrite, so composition of ferrite will be this one. What is the composition of Fe3C? This will be the composition, sorry, this will be the composition of Fe3C. So it is, and this point we know is 0.022%. So composition of the ferrite phase is this, and composition of cementite phase is 6.7%. As simple as that. What was the second part of the problem? Second part of the problem was you have to find out how much is the cementite present if 100 gram steel is there. So basically let us find out what is the fraction of cementite present in this mixture. What is the fraction of Fe3C present? That you have to find out. Okay. So how we can find out that? We know by using the lever rule. So the problem is we have to find out the amount of cementite or the iron carbide if 100 gram is the total. Okay, so let us first find out the fraction, then if you multiply it by 100 you will get the exact amount in gram. Okay, so Fe3C amount you have to find out divided by Fe3C plus alpha, that is the total mixture. Okay, this is what is the weight fraction. So what is weight fraction, you tell me? Weight fraction we can easily find out. We have to find out the weight fraction of cementite. If we have to find out the weight fraction of cementite, then we will take the opposite term, if you remember. So what is the opposite term of Fe3C? This, that is R. So it will be R divided by R plus S. This is what is the weight fraction. Okay, so what is R? R means this composition minus this composition. What is this composition? CO. What is this composition? CO alpha. CO is 4.4%. This is 0.022. So 0.4 minus 0.022. This is what is R. Divided by the whole length from here to here, which is R plus S. That means this composition minus this composition. That means 6.7 minus 0.022. So this is what is the weight fraction. If this is the weight fraction, then what is how much cementite is present in 100 gram of steel? Simply this weight fraction multiplied by 100 will give you how much the cementite is present. Similarly, you can find out how much ferrite is present. In that case, you have to take the opposite term, that's all, or you can simply subtract from the 100, you will get the answer. Okay. Now the third part of the problem. The question was, find the amount of pearlite and pro-eutectoid ferrite. Okay, so that you have to find out. Now see, if you see this diagram, you just think of before coming to this eutectoid, just above the eutectoid composition, just above the eutectoid composition. So at that position, what are the two phases present? Tell me. If you draw a tie line, the two phases present was ferrite and austenite, right? Because these are the two phases present. Now we are thinking just above the eutectoid. Now this austenite part, when you are further cooling, this austenite part actually forming the pearlite, right? And this ferrite part that already has been produced is called the pro-eutectoid ferrite. So basically you have to find out that what is the amount of austenite just above the eutectoid, that's all, because that part actually converted into pearlite. Okay, so what is the composition of that? That is basically 0.76. What is the composition of that? That is 0.022. Okay, so you can find out by lever rule what fraction of the pearlite and what fraction is austenite, what fraction is ferrite. So now in this diagram, see, we are here, just consider this is what is the austenite. So what is the fraction of austenite? If we want to find out the fraction of austenite, that means W alpha. So austenite fraction will be just we have to take the opposite term. What is the opposite term to austenite? That is R. R by R plus S. That is the total weight. Okay. And this austenite, remember, actually converted into pearlite. So this is nothing but what is the fraction of pearlite present. What is the fraction of pearlite present? This is all the same. These and these are same. So now you can easily find out that what is this R? This composition minus this composition. And what is R plus S? That is this composition minus this composition. So then we can find out how much is the what fraction is pearlite. So what fraction will be pro-eutectoid ferrite? Simply we will subtract from 1 and we can find out that. So you can see this is the overall composition, the composition of ferrite, composition of pearlite. So here it has been found out. Considering 100, you have to just multiply by 100 because it is given that the total steel is 100 gram. That's why 100 is multiplied. Otherwise, this is what is the fraction. What is the fraction present? And this is how much austenite present. Because how much austenite present is same as how much pearlite present. Because austenite actually converted into pearlite. So you can find out the pearlite present because austenite is same as, because the austenite will be converted into pearlite. So that is what is the pearlite fraction, and finally this is the pearlite amount. So pro-eutectoid alpha will be the remaining portion. Okay. Now here you see that the effect of the other alloying elements in the steel. Till now what we have discussed is the plain carbon steel. With iron only carbon is present. Okay. But if the other alloying element is added, then how the phase diagram is influenced by them, that you can see in these two graphical representation. Here you can see the eutectoid temperature. So in a plain carbon steel, what you have seen, the eutectoid temperature was 727 degrees centigrade, right? So here you can see, if you add titanium, molybdenum, or silicon, or tungsten, you see that with the increase of the alloying element, gradually the eutectoid temperature is increasing, or even it can increase up to more than 1000 degrees centigrade for a large fraction of these alloying elements. Okay, but in case of nickel or manganese, you can see the eutectoid temperature is decreasing. Okay, so this is one observation. Another one is the eutectoid composition. So in a plain carbon steel, what eutectoid composition we have observed? In a plain carbon steel, eutectoid composition was 0.76, right? But with the alloying elements, other alloying elements other than carbon, you see their effects. So with the increase of silicon, chromium, nickel, you can see the eutectoid composition is basically decreasing. So it is going from 0.76 to 0.6, 0.4, even lower than that for very high percentage of nickel, manganese, or chromium. Okay, so these are basically the effect of alloying element in the iron carbon equilibrium phase diagram. So finally, in this two part of the phase diagram, what we have seen is that they are very useful tools to determine the number and the types of phases, okay, and their wet fraction, and we have seen that how we can find out the phases, their composition, their wet fraction, right? And the composition, these things. How can we find out the composition? If you remember, you can find out the composition by drawing the tie line in a two-phase region. You can find out the wet fraction by the lever rule. Okay. So for a given temperature and composition of the system, that these things we can find out. Now, alloying to produce a solid solution usually increases the tensile strength. That we have seen in the first part of the phase diagram, if you remember the last slide. Okay, and the ductility decreases. And we have seen many binary systems like Eutectic, Eutectoid. Okay, and we have also seen that how the microstructure changes with the as we are cooling. Okay, so thank you.